more personal. Okay, so thank you all for coming, and we're delighted to have Robert back for the second of two talks. For slight background, to repeat from last time, Robert obtained his BSc Engineering and PhD Physics from the University of the Witwatersrand. He completed a year of postdoctoral studies at Brown University before returning to the University of the Witwatersrand. Gosh, you'd think I haven't been in this country for 15 years. Okay, from 2007 to 2022, he held the DST NRF Research Chair in Fundamental Physics and String Theory. Since 2022, he is a distinguished professor and Chang-Jiang scholar in Huzhou University in Zhejiang Province, China. His most recent research interests include the gauge theory of string duality, the application of representation theory of discrete groups, and Lie groups to quantum field theory of deep learning. And I think we're all saying this for everybody. Really excited to hear about black hole microstates. Please, Robert, when you get a chance to take it away. And I imagine, like last time, questions at any time?
Yes, please. Any questions that arise, please do ask. Okay, we don't have to finish the talk, so please ask any questions at all. Wonderful. Okay, so thanks very much, Will. Just for reference, the work I'm going to be talking about today was reported in a recent paper with Anton Levitsky from Brown University, and that's the archive number in case you want to take a look. Okay, so what was this work motivated by? It was motivated by something known as fortuity, a relatively recent discovery. So by studying 1/16 black hole microstates in ADS5 cross S5, the entropy of the black hole was reproduced by calculating indices in n is equal to 4 super-Yang-Mills theory. What this meant was you should be able to find a number of black hole type operators, so operators with the correct quantum numbers, that if you counted them and took the log of the number of operators, you should reproduce the black hole entropy, and that was n squared. The real puzzle was the equation you were meant to solve is this charge Q acting on the black hole operator was equal to 0. So this is the equation you had to solve. And when you worked out how many solutions there were to that equation, there were way too few solutions. So we just couldn't explain the black hole entropy. The big breakthrough was made rather recently. I'm going to be bad with references, but this is one reference I did want to include, by Chang and Lin in this archive paper. And they put forward something that was, I guess we should have known this long ago. What they said is if you want to solve this problem, Q on O is equal to 0, you could try to solve it for all n, and that they call monotone operators. And this QO equal to 0 for all n is what we had been doing since supersymmetry was discovered. But what Chang and Lin said is, well, maybe there are some solutions where Q acting on the black hole operator is 0 only for some specific n. And if you go above n star, Q acting on the black hole operator is no longer 0. So monotone operators solve the equation for the black hole operators for all n's. The fortuitous operators only solve it for a very specific value of n. And an enormous number of new solutions were discovered. Not surprising. If you want Q on your operator to be equal to 0 for all n, that's a much more restrictive condition than Q on your operator is 0 for only n is equal to n star. So there's a lot more fortuitous operators than there are monotone operators. And in fact, there's enough of them to explain the black hole entropy. More than that, the properties of these operators were studied, and it was discovered that the fortuitous operators are a lot more chaotic than monotone operators. Specifically, something called the Taoist time was calculated. So imagine that you calculate a two-point correlation function. One of the things that you can detect from this two-point correlator is when the motion transitions from purely ballistic motion, so moving in a straight line, to something chaotic, where you're being kicked around all over the place. The transition time from going from purely ballistic, so moving in a line, to the chaotic type dynamics, that's called the Taoist time. For a fortuitous operator, the Taoist time is order 1, whereas for the monotone operators, the Taoist time is the order of n squared. So fortuitous operators are a lot more chaotic than the monotone operators, and we expect black holes to be a lot more chaotic. So the recent insight, this is maybe a year, 2 years old, is that we should be looking for fortuitous operators. These are dual to black hole microstates. But the logic that led us here by Chang and Lin had nothing to do with supersymmetry. In fact, we know that black hole operators should have roughly order n squared fields. So let's say that you were studying the gauge theory with gauge group SU 10, so n is equal to 10. If you then wanted to build a black hole microstate, you'd give me some operator that has 100 fields in it. It would be some multi-trace operator, some sum of terms. If I go away and study that operator in the n is equal to 100 theory, I would discover the operator that you've given me is not a black hole operator. The operators that form black hole microstates in the n is equal to 10 theory are not black hole microstates in the n is equal to 100 theory. And that's similar to this logic that you see for the fortuitous operators. We satisfy the black hole operator for n is equal to n star, but not above n is equal to n star. But this last argument in particular has nothing to do with supersymmetry. So it makes us question, are black holes really present in the n is equal to infinity theory? Or should we rather be studying the theory at a large but finite n? And secondly, isn't this fortuity mechanism true for non-supersymmetric theories? It's much more interesting if we can say it's a non-supersymmetric theories because that's closer to the real world. And my goal in today's talk is to try to convince you that this fortuity mechanism really is present in non-supersymmetric theories, purely bosonic theories. So my approach to this problem, what's the question I'm going to try to answer? It's the following. I'm going to study matrix quantum mechanics of d n by n Hermitian matrices. So my matrices are called phi A. Phi A is an n by n matrix, and A goes from 1 to d. For each matrix phi A, there is a conjugate momentum, pi A. This is also a matrix. And the usual commutation relation that you're used to between position and momentum becomes now a commutator between the matrix pi and the matrix phi. And we have this commutator sitting here. Sorry, I spotted a typo on the right-hand side here. We should have a delta AB as well, okay? So there's a delta AB missing on the right-hand side of this commutator. I was focusing on the color indices, and you can see that the color indices contract in some non-trivial way. This model has a UN symmetry. I can replace phi A by U dagger phi AU, and pi A by U dagger pi AU, and the Hamiltonian is invariant. I am going to declare this to be a gauge symmetry. And what I'd like to work out is, what is the complete space of gauge invariant operators? Well, it's quite easy to know what it is. It's going to be the trace of products of these matrices. So you can take a product of phi 1, phi 2, all the way up to phi 6. Any matrices sitting inside the trace, take a trace, and that space of all possible traces is the space of gauge invariant operators. And what you can see is that this really is quite a complicated space. Let's see. Good. So what is the complete description of this loop space? And in particular, I would like to know, how do I generate this loop space? To really make sure that the question is clear, I would like to start with a single matrix warm-up problem. So if I've got a single matrix, I can diagonalize it. It's an oscillator problem, and I diagonalize it as usual by, sorry, let me just hide this panel. Good. I can diagonalize it as usual by introducing creation and annihilation operators. Now, you're probably used to A dagger being X minus IP. It's the same thing here. A dagger would be matrix X or matrix phi minus I pi. So just the position minus I times the momentum. The Hamiltonian up to a ground state energy is 1/2 trace of A dagger A. And because it's a simple oscillator, I can easily calculate the partition function. And what this partition function looks like, z of x, is 1 over 1 minus x, 1 minus x squared, all the way up to 1 minus x to the n. I should have told you what x is. Sorry, that was an oversight. X is e to the minus beta, where beta is the inverse temperature.
So I have a question, Ron.
Yes?
Yeah, so your position operators and momentum operators are both, I don't know, say n by n matrices.
Yes.
Your sorry, position. Yeah, okay, so these operators that you talk about, are they also the same kind of dimension matrices? Is it the
So X would be an n by n matrix, pi an n by n matrix, and A itself an n by n matrix.
oh, okay. And like the states or what?
Mhm.
So here the states would be, so you would take a dagger, you would act on the vacuum, and any states that are invariant under the UN symmetry would be an allowed physical state. So I am declaring, let me see if I can go back. I don't know how to go back, but I am declaring that any UN invariant state is a physical object. So let's see if I can.
I guess the question is, what is the Hilbert space? And I guess it's an n-dimensional complex vector space.
So the Hilbert space would be, take these gauge invariant words, these traces of all of these phi's, okay? Or you could take traces of A daggers, act on the vacuum of the Hilbert space, and that would be the Hilbert space. What I'm going to do soon is give you a description in terms of a Fock space.
Wait, so you're acting not, so the operators are these n by n matrices, which in principle could act on an n-dimensional complex vector space, but because you're taking these traces, your vector space is actually just a one-dimensional complex vector space?
So we're going to see soon it's n-dimensional, but that shouldn't be manifest right now. So in the same way that the vector field had 4 components, and then after gauge invariance, only 2 of them were physical, here after gauge invariance, we're going to be able to see what the actual physical degrees of freedom are.
Oh.
This n-dimensional vector with the matrices acting on it, that's not a gauge invariant notion. We'll get to what a gauge invariant notion is soon. Okay, does that answer the question?
Yeah,
Good.
great. Sorry, one more thing. What was the x here? It's e to the minus beta.
E to the minus beta. Yep.
Well, beta is dimensionful, right? So e to the minus beta times something.
Yes. Put in Boltzmann constant where you like.
All right.
Okay. Good. Okay, so how do we interpret this? Well, the way that we interpret it is each factor in the denominator corresponds to an operator. And x to the n corresponds to trace a dagger to the n. Now, this might seem a bit puzzling. Let's, for example, say that n was equal to 2. If n was equal to 2, you'd only have 1 over 1 minus x, 1 minus x squared, and then it would truncate. So the only gauge invariant operators that we would take would be trace of a dagger and trace of a dagger squared. But what about something like trace of a dagger cubed and even higher powers? Those are also allowed. And where those come from, those are the trace relations that we discussed last week. So remember, for any 2 by 2 matrix, there's a relation obeyed by all 2 by 2 matrices. It takes the form that's given here. And just maybe to jog your memory and talk about it in a slightly different way, when you're taking traces of powers of M, it depends on the eigenvalues of M. And because M is a 2 by 2 matrix, there are only 2 eigenvalues. So once I've told you trace of M and trace of M squared, you know everything. So you would know in particular what was the trace of M to any power. And in fact, using this trace relation that's sitting here, setting M equal to a dagger, we can write the trace of a dagger cubed in terms of trace of a dagger squared and the trace of a dagger. So if you had n by n matrices, as long as you had the trace of a dagger squared, going all the way up to trace a dagger to the n, you could write the trace of a dagger to any power using the trace relations. So what did this one matrix example actually show us, it showed us the following. We only need trace of a dagger squared, all the way up to trace a dagger to the n. And those things, after you multiply them, will generate every single gauge invariant operator that you can think about. So what I'm going to be doing in the rest of this talk, I'm going to be calculating the partition functions, so the analog of the first formula on this slide, but I'll be doing it for more than one matrix and at a given n. And then I'm going to interpret those partition functions. And my goal is going to be to use the trace relations and argue to you that we can write every single gauge invariant operator using the trace relations. So that's going to be the goal. To calculate these partition functions for D matrices, I'm going to be using a very nice math formula. It comes from the theory of graded rings, and it's called the Moline-Weil formula. But they're really calculating a partition function. I'm always thinking about a free theory because their energies are additive, but the trace relations, which is all that I use, holds for the non-interacting theory too. So even though I'm thinking about the free theory when I derive this Moline-Weil formula, just remember this will be true for interacting theories too. And we'll discuss that a bit more as we proceed. If we want to calculate the partition function, what would we do? So here we've got x is equal to e to the minus 1 over t, or e to the minus beta. The partition function would be take n1 copies of the first matrix, n2 copies of the second matrix, n3 of the third, and so on. Count how many singlets you can make out of those matrices, and weight that by x to the n1 e1, x to the n2 e2, and so on. And then do the sum. That would give you the partition function, nothing fishy. We've just got the Boltzmann weight, the e to the minus beta times the energies times the number of states. So that's what you'd always do. The first step in the Moline-Weil formula comes from noticing that the number of singlets in this tensor product, so we're taking a symmetric product of n1 copies, symmetric product of n2 copies, all of the adjoint representation, because our matrices are bosons. So we must take the symmetric product because we've got bosons. We've got this tensor product because those are the fields that we're using. And the claim is the number of singlets that appears here can be rewritten as an integral over un. So I want to motivate that a little bit because that's maybe the key step that's going on here. If I've got a product of fields and the ith field transforms in representation Ri, then a product of k of these fields will transform in a representation R1, tensor R2, tensor, keep going till tensor Rk. So that's going to be the representation of the product of these fields. The character of a tensor product representation is simply the product of the characters. So I have a character for R1 tensor R2, it's the character for R1 times the character for R2. Where does this formula come from? Remember that the character is just a trace, and the trace of A tensor B is trace A times trace B. So if we've got a product of fields, the character associated to that representation is going to be the product of the character for each field. Now, in general, if we take a tensor product of many representations, this representation is reducible. So it'll be a direct sum over some representations RL, and representation RL can appear an integer number of times, which I've called NL. So NL is the number of times that representation RL appears. And to determine NL, we use the orthogonality of characters. We take the character of the tensor product times the character of RL, and we integrate over the group. Okay, I should probably have called all of these G's to be U's, and we just integrate over U. For the singlet, the character is just 1. So using that logic, this is what our partition function becomes. It's now an integral du, product over I. We have to still do these sums, and we've got this character for this symmetric product of n copies of the adjoint, because all of our fields are in the adjoint. There's a very useful character formula that I'm going to use. This you can prove by Gaussian integration together with Wick's theorem. So I haven't gone through it. I'm just going to use this formula. but it allows me to write the sum as the exponential of a sum. And using that in total, my partition function becomes an integral over un of an exponential and a bunch of adjoint characters of u raised to the power of m. So I now need to do that matrix integral. Now, there's a standard way to do these matrix integrals, integrals of a single matrix. We transform to the eigenvalues of the matrix. Because we're dealing with a unitary matrix, all of these eigenvalues have magnitude 1, so that after we replace integrating over the matrix to integrating over the eigenvalues, we're integrating over a bunch of unit circles in the complex plane. Because everything only depends on traces of u to the m, the integrand only depends on the eigenvalues. So I can do the integral over the angular pieces of the unitary matrices. And after I've done that, the integral over du becomes some constant times an integral over the eigenvalues and a product of two Vandermonde determinants. And I've given you the expression for the Vandermonde determinant here. You shouldn't be able to follow all of these details from what I've showed you. I just want to show you that this is an honest formula. So I'm just walking you through what we do to get to the Moline-Weil formula. So the partition function now reduces to this form. So what happened here? You see, look at the sum, the 1 over n with these characters. The character becomes the eigenvalues to some power. We've got x to some power 1 over m. Well, you know what 1 over m x to the m is. When you sum that series, you're just going to get a log. And the exponential of the log just gives you whatever sits inside the log. And that's where these fk's have come from. And these fk's are very simple formula sitting over here. And z is just some normalization bit sitting up front. I do one more change of integrals. I set the j's eigenvalue equal to a product from t1 up to tj. And Weil noticed this. So it wasn't me, it was Weil who noticed this. The change of variables here is associated with this Jacobian, which is easy to calculate. And then the partition function takes this remarkably simple form. One last simplification, as the Tn only appears as 1 over Tn. So we can do the integral over Tn to get the last formula on the slide. Okay? Weil derived it. We can trust it. This is the formula that we're going to use for the rest of this talk. I just wanted to sketch to you how it's done. The partition function is written in terms of the number of singlets. That can be written as an integral over a unitary matrix. You can transform to eigenvalues, and after a change of variables, you get the formula that I show you. This is the exact partition function. We're going to evaluate this formula using the residue theorem. We're only going to pick up residues inside the unit circle. So this is a lovely problem that you can put onto Mathematica. We can introduce chemical potentials to keep track of the different species of fields, and the formula will apply for any number of matrices in the matrix model. If I introduce chemical potentials, let me show you there's one thing that changes. When we look at this original formula for z of beta, for the first matrix we would use an x, for the second matrix we might use a y, for the third matrix a z, and then the partition function will be a function of x, y, z, and so on. One letter for each different matrix. So I'm just using this formula to evaluate the partition functions. Okay, so for two matrices, n is equal to 2. I use that formula. I've graded it in terms of x and y. And this is the answer for the partition function. So we've got a 1 over 1 minus x. What does x, this 1 minus x, correspond to? Well, this x is actually trace of some matrix, which I've now called x. The y here corresponds to trace of a matrix y. And you see, it's so nice that it's graded because I can read off what each of these factors correspond to. So x squared is the trace of x squared, xy is the trace of xy, and y squared is the trace of y squared. What does this answer mean? Well, just like in the single matrix case, it means every single gauge invariant operator that I could think of writing down can be written as a product of M1 through M5. So we're going to take products of M1, M2, M3, M4, M5, and that will give us every single gauge invariant operator. And that's what I want to prove to you now using the trace relations. What is the trace relations for n is equal to 2? for 2 by 2 matrices? Well, it's the statement that here for 3 matrices A, B, and C, this particular sum of the matrices vanishes. So trace A times trace B times trace C minus trace AB trace C, and those other 4 terms, if you sum them, you will always get 0. And A, B, and C can be any words constructed using X and Y as letters. And you'll see some examples of this soon. So let's consider words of length 3. So words of length 1, we've got trace X, trace Y. Those are all of the words of length 1. For words of length 2, all we can have is X squared, XY, and Y squared. So we've got all words of length 1. We've already got all words of length 2. So now let's look at all words of length 3. I'm going to talk about NX fields and MY fields. When M plus N is equal to 3, any choice of M and N gives us a single trace relation and a single gauge invariant operator. And that single trace relation determines the gauge invariant operator. So let me give you an example. If M is 2 and N is 1, the only gauge invariant operator you can write down that is a single trace built from 1x and 2 y's is the trace of xy squared. And that's because by cyclicity of the trace, this is equal to the trace of y xy, and it's equal to the trace of y squared x. So this is the only operator you can write down. If you plug A is equal to x, B is equal to y, and C is equal to y inside our trace relation, you get this sum of terms is equal to 0. Well, the first 3 terms over here have at most 2 matrices inside the trace, so they can all be written in terms of M1 up to M5. And that means that the trace of xy squared is 1/2 and this combination of the m's. So using our generating set, I've now generated trace xy squared. Swapping x and y, we get trace yx squared. In fact, all traces with 3 matrices inside the trace, it's easy to verify they're all written in terms of our M1 up to M5. Let's now go to 4 matrices inside the trace. Now here something new happens. You see, we want M plus N equal to 4. And if we set M is equal to 2 and N is equal to 2, now we can construct 2 different operators with 4 matrices in the trace. We can get trace x squared y squared, or we could get trace xy xy. Fortunately, there are 2 independent trace relations. We can set A is equal to y squared, B is equal to x, and C is equal to x, and this allows us to solve for trace x squared y squared. Or, and this gives us a different trace relation, we could set A equal to xy, B equal to x, and C equal to y, and with this trace relation we can get trace xy xy. So we were lucky. We were now able to construct 2 distinct gauge invariant operators, but we found that there were 2 distinct trace relations that we could use to solve for those operators. Does this pattern continue? In particular, you'd need to show that the number of independent operators is matched by the number of independent trace relations. Does this really continue? So I want to prove to you now that yes, it does.
Sorry, I have a question.
Sure.
When you're looking at these trace relations,
Yep.
for example, you said you've got 2 independent ones here. Maybe it's a silly question, but the actual things that you insert into your trace relation, for example, in the second one there, you've got x, y, and then x and y as independent arguments. Is there not some other order you could put them in? Why specifically that order? Are all things equivalent, or do they just give you non-independent relations?
So that's a great question. Okay, counting trace relations is not trivial, but let me motivate for you why this works in this way. The term to look at the term here, which is trace of A, B, C. So focus on that term, trace of A times B times C. You can see that from this trace relation, trace of A times B times C is y squared x squared. So we naturally get a trace x squared y squared. The other thing that we can have is a trace ACB. And for this one, the trace of ACB is also trace x squared y squared. So both of those single trace terms are exactly the trace that you have sitting here. But when you look at this trace sitting over here, if you take xy times x times y, now you get the trace of xy, xy. If you take the trace of xy times x, you're going to get a trace of x squared, y squared, but you know how to write that from the relation above. Okay? So at this stage, I'm not doing anything sophisticated about counting trace relations, which actually is a non-trivial problem. But just by inspection, by looking at the trace relations that I've got, I know there's two of them. I know that they're different. One of them involves only trace x squared, y squared. The second one also involves trace xy, xy. So between the two of them, that's enough to solve for these two gauge invariant operators. The question you ask, how do we count the number of independent trace relations? How do we know they're independent? That's a great question. It's a harder question, and I'm going to not answer it. Is that okay?
Yeah, that's fair enough. All right, thank
Good.
you.
Sure. So now what I want to do is, I want to argue that any gauge invariant operator can be written in this way. I'm going to prove it by induction. So I'm going to prove that if you've got at most k matrices in the, if you can write everything with k matrices in the trace, in terms of our generating set, then I'm going to prove to you that that's enough to prove with k plus 1 matrices inside the trace, we can also succeed. And then the induction proof works because we've already proved that our statement works for k less than or equal to 4. So let's start off. This is not the most general loop. This is a specific loop, but it's a loop that I want to look at. Let's look at trace of x to the n1, y to the m1. And let's assume that n1 plus m1 is equal to k plus 1. So now we've gone to k plus 1. And we'll take k to be greater than or equal to 4. So these two integers must sum at least to 5. So that means one of them, either n1 or m1, must be bigger than 1. Let's assume it's n1 that's bigger than 1. Then I'm going to choose a to be x, b to be x to the n1 minus 1, and c to be y to the m1. I plug it into my trace relation. What do I get? Well, the first term is exactly the loop that I'd like to determine, that is k plus 1 matrices inside the trace. What do all of the other loops look like? All of the other loops always have at least k, this has got k inside the trace, or less. Every single other term would have less than k matrices inside the trace. So this proves that trace of x to the n1, y to the m1 can be written in terms of our generating set, because anything with k or less matrices in the trace by the induction hypothesis can be written in terms of our generating set. Now let's look at a much more general loop. X to the n1, y to the m1, carrying on up to x to the nq, y to the mq, where the sum of these powers is again k plus 1. Let's call invariance with x to some power, y to some power blocks, with q of these blocks in it. Let's call that a type q invariant. So the loop that you see at the top here, we've got x to a power, y to power keeps going, x to nq, y to mq. This is a type q invariant because we've got q of these xy blocks appearing. Now let's look at the trace relation that you get from a is equal to x to the n1, b is equal to y to the m1, and c is equal to x to the n2, y to the m2, going all the way up to x to the nq, y to the mq. So if I plug in and look at the trace relation, what do I get? The second two lines of the trace relation never have more than k matrices inside the trace. So the second two lines I can always write in terms of my generating set. The first term in this relation is a type q invariant, and the second term in this relation is a type q minus 1 invariant. So if we knew the q minus 1 type invariant, we would know the type q invariant. But I proved to you on the previous slide that we know the type 1 invariant. So if we know the type 1 invariant, we know the type 2 invariant. But if we know the type 2, we know the type 3, and so on. So in this way, we can generate every single trace with k plus 1 matrices inside the trace, as long as we can write traces with k matrices inside the trace in terms of our generating set. So sorry, this was the only detailed proof, but I just wanted to show you that we really can write every single gauge invariant operator in terms of our generating set those 5 traces that we had. And now here's the important question. What's the important lesson? The complete space of gauge invariant operators can be expressed as linear combinations of these 5 invariants raised to an arbitrary power. Well, this looks like a Fock space structure. It looks like you've got 5 creation operators and you're allowed to raise them to any power. And this will give you every single state inside the Fock space. How should we interpret this? Well, according to the gauge theory gravity duality, we expect all gauge, this is not proved, but we expect that all gauge theories are dual to some gravitational theory. The gravitational theory should have a loop expansion parameter of 1 over n. Now, there's a systematic way to change variables in the field theory and write the field theory in terms of these variables. That's called collector field theory. And the loop expansion parameter of the collector field theory is 1 over n. So this collector field theory is a constructive way to build the gravitational theory. And it's natural to conjecture that the Fock space that we found here is the Fock space of the dual gravitational theory. So we've discovered a Fock space by reducing to the gauge invariant sector of the theory. This is not, however, the complete story. Now we'll get the complete story with 3 matrices at n is equal to 2. And when we calculate this partition function, again using the Moline-Weil formula, well, we have these products of terms in the denominator, and these, again, because it's graded, can nicely be identified with some traces. Inside every single trace, we have at most 2 matrices appearing. And then in the numerator, though, we have 1 plus some additional term. And again, because this is graded, we can view this additional term as a trace of x, y, and z, our 3 matrices, a product of the 3 of them. The things in the denominator correspond to what are called primary invariants. The object in the numerator is called a secondary invariant. When you act with the secondary invariant, you're allowed to raise it either to the power of 0 or to the power of 1. But you're not allowed to consider the secondary invariant squared. And the reason for that is there's a very interesting constraint that appears. The secondary invariant squared can be written as the secondary invariant times some polynomial in the primary invariance plus some polynomial in the primary invariance. So to generate the full space of gauge invariant operators and to get a complete description, not an overcomplete description, you should never consider s squared. Only s to the 0 or s to the 1. So this is the complete space of gauge invariant operators now. It looks like we've got these 9 Fock space type operators. So these 9 invariants we can raise to any power times by 1. Or we could take these 9 invariants raised to any power times by s. And that, again, you can prove exactly using the trace relations like what I did before. You can prove that this is a complete description of all gauge invariant operators in the theory. So what is this S doing? This S is creating a non-trivial state that can support perturbative excitations. Now, for those of you that have studied solitons, you're used to thinking about the soliton as a non-trivial solution to the equations of motion, and you're allowed to have perturbative excitations on top of the soliton. This S, we called it S for a reason. It's reminiscent of a soliton. You should think about this S as some non-trivial state in the theory, and you can put perturbative excitations on top of that solitonic state. This form for the partition function, the fact that we had a sum of terms in the numerator that had all positive coefficients, and this product of factors in the denominator, this is called a Hironaka decomposition of this partition function. So it's known in mathematics. And a few things that are known from the theory of graded rings, all of our partition functions are going to take this form. The number of factors that appears in the denominator is always d minus 1 times n squared plus 1. And there's some serious mathematics behind this. Because we're looking at GLN invariance, we can prove this is a Cohen-Macaulay ring. Because it's a Cohen-Macaulay ring, there's always a Hironaka decomposition. So this form of the partition functions will always take this structure. Now, let me show you some physics from this. So our partition function will take this form. Let me show you some physics. When we go to very high energy, we expect to be above the deconfinement transition. And in that case, we would expect to be able to discern all n squared degrees of freedom. So how do our partition functions behave as we take the high temperature limit? The high temperature limit corresponds to taking t to infinity, so beta to 0. Since x is equal to e to the minus beta, we're taking x to 1. So if we work out what does our partition function do, the numerator is a polynomial with just positive coefficients. If we take x to 1, this goes smoothly to some number. And in the denominator, if we take x to 1, 1 minus x to the power of n minus 1 just goes to ni times 1 minus x. So the limit as t goes to infinity of our partition function, which is the same as taking x to 1, is just some constant times the temperature to the power of d minus 1 n squared plus 1. So free energy is just minus t log z. We know z, so that's very easy to calculate. And if we now calculate the entropy, which is minus df dt, we can see explicitly that the entropy goes like n squared. And this is exactly the behavior that we expect above the deconfinement transition. Okay, there's a comment on the primary invariance. So we know that if there are less than n matrices inside the trace, they must be included amongst our invariants because there are no trace relations that would allow us to solve for traces of fewer than n matrices. How many operators are there with fewer than n matrices inside the trace? Well, a very accurate estimate of the number of operators with L matrices in the trace is D, the number of species of matrices, raised to the power of L divided by L. It's a systematic underestimate, so it's an underestimate at every value of L. But if you plot the actual value of L against this estimate, as soon as L gets appreciable, the naked eye cannot distinguish between the two curves. So if we're looking at operators that have got n matrices inside the trace, how do they grow? They grow like e to the power of n. The number of primary invariants grows like d minus 1 n squared plus 1. This is what the mathematicians have told us. So if you look, for example, two matrices at n is equal to 20, so this is an exact count of the single trace operators. There's 111,321 of them. Only 401 of them are primary invariants. So most of them appear as secondary invariants. I think this was a bit of a surprise. In my community, people were used to saying you should take all single trace operators with less than n matrices inside the trace. That turned out to be completely wrong. Only a very small fraction of operators you should keep, and most of the others appear as secondary invariants. How do the secondary invariants grow? So this was done just by looking at the number of operators that we have. Now look at this. We've increased n from 2 to 7. The number of primary invariants goes from 5, 10, 17, 26, 37, 50. That's a very modest growth. It's growing like n squared. Look at the number of secondary invariants. So this we got by explicit computation. 0, 1, 63, 15,000, 312 million, 21,000 billion. That's an American billion, not a British billion, but still 21,000 billion in that last line. So the growth in the number of primary invariants is n squared plus 1. The growth in the number of secondary invariants is much more rapid than a power. So from these 7 numbers, can we kind of guess how the number of secondary invariants is growing? Well, if we make the guess that the number of secondary invariants is going like e to the 1,1 n squared minus 3,3 n, then this orange curve here is the log of our guess for n secondary, and the blue curve is the log of these numbers that you see sitting here. And they match very well. So our numerical results at least give us some plausible evidence that the number of secondary invariants is growing like e to the power of n squared. But if you take the log of that, you get n squared, which is exactly the entropy of the black hole. So the number of secondary invariants, which we said was non-trivial, solitonic-like states, the number of states is growing to match the black hole entropy. So this is what we claim is our analog of bosonic fortuity. Recall that the operators that are dual to black hole microstates at some n, which obey QO is equal to 0, are not dual to black hole microstates at a larger value of n, where QO is not 0. An operator that represents a black hole microstate in the n is equal to 10 theory does not represent a black hole microstate in the n is equal to 100 theory. If you increase n and you just look at the partition functions that we've calculated, we find that as n gets bigger, more and more of the secondary invariants change their character and they become primary invariants. So more and more of these states that look like non-perturbative solitonic type states that we want to interpret as black hole microstates, they change their character and become perturbative degrees of freedom. So this is what we are postulating as a purely bosonic analog of the fortuity mechanism. So the fortuity mechanism that was discovered in supersymmetric gauge theories, we claim is also present in the bosonic gauge theory, and the way that you see it is by doing a complete gauge fixing of the theory. At infinite n, there are no trace relations for any operator, because these only kick in when there are n plus 1 matrices inside the trace. And if n is infinity, you need infinity plus 1 matrices inside the trace. So the large n limit, the partition function, takes the form that you see sitting over here, and there are no secondary invariants. All of the secondary invariants have now been promoted to primary invariants, and there are no black hole microstates at n is equal to infinity. And this is something that we have been led to suspect recently by progress on black hole microstates. So now, how does collector field theory sit into this? So this is content of a paper that will appear soon. So collector field theory provides for you a completely consistent way of thinking about the n is equal to infinity theory before you impose any trace relations. The trace relations you can check are constraints that commute with the Hamiltonian. So you're able to impose those constraints and get the theory at any finite n. The loop expansion parameter of collector field theory is 1 over n. This matches the loop expansion parameter expected of the dual gravity theory. And something that we've been claiming for a while now is that collector field theory provides a constructive approach to the gravitational dual theory. So an interesting open question, something that's well worth pursuing, is to see how you can recover the dynamics of black holes and some of the properties that we know of black holes from the dynamics of these secondary invariants of this overcomplete theory. Okay, so let me just summarize now what I claimed that I have demonstrated. So we've described the space of gauge invariant operators at finite n. We found that to generate the complete space of gauge invariant operators, you need primary operators and secondary, primary invariants and secondary invariants. The primary invariants give rise to a Fock space structure. You can raise them to any power when you're constructing the space of gauge invariant operators, and you will not be overcounting. There are a total of d minus 1 times n squared plus 1 primary invariants if you're dealing with d species of matrices. The secondary invariants are naturally interpreted as non-trivial backgrounds. By the way, if you've got a secondary invariant S1 and a secondary invariant S2, you're not allowed to consider S1 times S2. That again can be eliminated in terms of terms linear in S1 and S2 and the primary invariants. You're only allowed to consider S1 or S2. And that's very much in line with our interpretation that S1 and S2 are both considered as non-trivial backgrounds or non-trivial states of the theory. We've given numerical evidence by studying the theory up to n is equal to 7, which is where we're able to go numerically, that the number of secondary invariants grows like e to the c n squared. And this matches the number of states that we would expect for a microscopic description of a black hole. So we claim that these secondary invariants are related to black hole microstates. we found a purely bosonic analog of the fortuity mechanism where secondary invariants transition to become primary invariants as n is increased. So something that would be a black hole microstate of a small n gauge theory is no longer a black hole microstate for a bigger n gauge theory. From this point of view, what is the Hironaka decomposition that the mathematicians discovered of rings? Well, it's a decomposition of the Fock space into a direct sum of excitations about these different backgrounds. So it has a very natural interpretation in terms of the gauge theory. Okay, and thanks for your attention.
Timing is incredible.
Thank you.
Questions for Robert? Yeah, Daniel, please go ahead.
I think I got a little confused on how the invariants change character as the size of n grows. You said that so if I have like a trace of two matrices, and then I push up the size of n, that changes from a primary
Yes.
secondary invariant.
Yep. So let me explain what evidence we have to make that statement. So I would love to give you a mechanism and explain to you how it happens and when it happens. Okay, so that's not the level of our understanding. So let me tell you what it is. So here I showed you the partition function for a 3-matrix model at n is equal to 2. I can also calculate the 3-matrix model at n is equal to 3. And what I will find is this term x, y, z, which at the moment appears inside the numerator, it flips, and now it becomes a term inside the denominator. So x, y, z still appears, but it becomes a factor in the denominator. So I'm confident in claiming that that secondary invariant became a primary invariant because I just calculated the partition function at n is equal to 3. Now, if you want an explanation for why that happened, well, it's related to this infinite set of equations that you get from the trace relations and solving those to get the complete set of gauge invariant operators. And it turns out that n is equal to 2, you only need to use x, y, z once, but at n is equal to 3, you're allowed to use it raised to any power. And I wish I had a simple explanation for that. I don't yet. That's one of the things that we're looking at to figure out, without looking at the partition function, how do you tell whether an invariant is primary or secondary and when it makes a transition?
And that's what the flipping of the invariance is what causes the growth in the number of black hole states.
You know, so so this number, e to the n squared, that was just obtained by staring at these integers. So could that be wrong? Yes, it could be wrong. But look at this growth. This looks a bit nutty, right? 63 to 15,000, then to 312 million, then to 21,000 billion. I mean, this looks like a crazy growth of states. So we did try to work for n is equal to 8. But I estimated that on my laptop, it would take about a month to run. So we were brave enough to try it. But after 3 weeks, Mathematica crashed. So we haven't put it running again, but it would be nice to get, well, a few more numbers if we could. But so far, we haven't managed to really see that this growth is like e to the n squared. What the flip does, that flip is absolutely necessary to get this nice form of the partition function at n is equal to infinity, where you say there's no secondary invariance. So some of the secondary invariants have all become primary, and we know for the n is equal to infinity theory, there are no trace relations, just everything is independent. So this form, equation 4, was known before. This was calculated previously before we even looked at this problem. So this is in line with the idea that all of the secondary invariants ultimately become primary.
And it looks really funny, right? If you look at your table with the two, right, the number of primaries goes up very, very slowly. And you have the secondary growing like crazy, but you're talking about converting secondaries into primaries. Wow.
So I tell you, so there's a few puzzles that have come up, I would say, in the last few years. So one of the things that people have been questioning is, does the large N limit of gauge theories really make sense beyond the planar limit? So we know the planar limit makes sense. And the thing that has been worrying people is that the dimension of the Hilbert space increases so rapidly that things like normal partition functions that you would calculate do not converge. You just have the sums just are over so many terms that you spoil the convergence. And this interest that you may have noticed has been very big in my community. I don't know how much it's spread out to others, but in terms of thinking about things like entanglement entropies, in terms of von Neumann algebras, all of that work has been trying to tame this massive growth in the dimension of the Hilbert space. So we have known about this massive growth, and people have started to question, maybe you cannot see black holes in the strict n is equal to infinity limit. And well, I would say that our picture fits very nicely with that intuition and supports that. And this crazy growth here is the crazy growth in the entropy that you expect of a black hole.
Sorry, the other crazy aspect is that, right, you increase the number of primaries, so your Fock space also explodes.
Yeah.
Your humongous tower of Fox, right, of Fock space is built on top of all your secondaries also grows. Like, I mean, this is
Absolutely. Yeah. Yeah. So we didn't expect this.
I mean, I get a big idea why you say it's a direct sum, because there is just the algebraic identities that you have to support this, right?
Exactly. Yep.
And they, as long as your numbers are finite, this is absolutely
Yeah.
You can't break that. It's
Exactly. Yeah.
correct as hell. So no. The interplay of these numbers makes no sense to me at this point. It just looks sick. I'm not doubting you, but
to us too. Yeah.
No, it's very it looks very promising. But,
yeah.
Wow.
Yeah.
Other questions?
I just have like a quick question about the nomenclature.
Yes.
The 1/16th BPS states that you're counting, that's in terms of n equals 4, right?
That's absolutely correct.
And that would be a quarter in n equals 2, right? In terms of that language.
Okay, don't do that to me. Don't Let me just tell you what the 1/16th means. So we've got a total of 16 independent supercharges. So the most supersymmetric state would be killed by all 16 of them. In this 1/16th case, only one supercharge kills the state. Jared, you'll be much better at translating to n is equal to 2 than I am. Also, I just had denied a glass of wine. I'm not going to translate to n is equal.
Okay. Yeah, it is just the language, because studying Schrödinger indices,
I
like
see.
you have the constant in change for the papers. I think I just need to make sure I'm checking things correctly.
Okay. Daniel, do you want to have a thought?
Yeah, I have a potentially very stupid question, because I haven't studied black hole entropy sort of at all. So when you talk about the invariance of this growing as n or log n squared, and that's matching black hole entropy, how can you be certain that that's the only thing that it matches? You want to make this claim that how do I?
Yes. Okay. So let me tell you, this is the evidence for it. And if you find this compelling, that's great. And if not, maybe there's another interpretation. But this is the idea. So Hawking and Bekenstein really figured out that black holes have this entropy which is the area of the horizon divided by g Newton. Now, g Newton in these gauge gravity models, that's like the loop expansion parameter, it plays the role of h bar, and that's 1 over n squared. In the gauge theory, you get an expansion of 1 over n squared. So you can think it's the area divided by 1 over n squared. And 1 over n squared is n squared. So that's why we expect the entropy to grow like n squared. Now, is there another object that's so entropic? So this is, of course, something that people have argued a lot. And the general consensus, I don't think there's a proof, but the general consensus is if you just go ahead and calculate entropies associated with different systems, black holes have a crazy huge amount of entropy. There's nothing that have as much entropy as a black hole. So really, one of the puzzles with explaining microstates is, where are you going to get e to the n squared states from? It's not easy to get that many independent states. So while we don't have a proof at all that this is related to a black hole, it seems implausible that it's related to anything else. If it is, we have to rethink a lot of other physics too. Let's put it like that.
Let me throw another one. I mean, you're counting secondary invariants in this game, but you have a whole you have a whole Fock space on top of each. So why do you why it's
okay?
Well,
good question.
Why do all these other states don't matter?
Okay, good question. So I think that the way to think about it is you've got this black hole sitting there. And even with the black hole sitting there, you're absolutely allowed to stick gravitons floating around in the space-time. Those gravitons floating around in the space-time, those would be your perturbative degrees of freedom. That's what the Fock space would be supplying. So you could have a black hole state sitting there with a whole bunch of gravitons just zipping around in space-time doing whatever they like to do. The counting of those gravitons which are allowed to zip around will be given to you by the Fock space piece. And then you need something else to give you the black hole entropy, and that's what the secondary invariants give you.
Not sure I'm really following you, but
so if you've got a state, so let's say you've got a soliton, for example,
Yep.
You're allowed to have perturbative excitations on top of the soliton. So if you've got a black hole sitting there, you can also have a gravitational wave that's zipping past that black hole. Acting with these Fock space operators is like creating gravitons on top of this black hole microstate geometry.
that move away from the black hole in a way, not part of it. Is that?
That's right. Yes. Yeah.
Okay. Yeah. Okay.
Okay. Other questions? I'm just kind of curious, a couple of questions. Have you just happened to throw in these sequences into the OEIS?
Yeah, we did. It doesn't recognize them.
Ah, well, you can add your own entries.
Absolutely. That's on my to-do list. Absolutely, Will.
And then maybe another question, perhaps similar to Daniel's question. Is it obvious that one can see a difference between e to the n squared growth versus a factorial growth?
Factorial growth is e to the n log n. So that is quite different to e to the n squared. So what we have also done, we've studied a model with n particles, and you've got permutation symmetry. So in that case, it's almost like having diagonal matrices. And in that case, the growth is e to the n log n. So like n factorial.
And then maybe a last question. So this is a sort of you've got time but no space.
Yeah.
Do you think that there's any hope of finding some 1+1 dimensional ADS-ish thing that could be dual to this?
That would be amazing if we could do it. So I'll tell you what problem you have to solve. And so I don't know, maybe somebody with more insight than me could do this. I don't think I could. It's really the following. This index A that sits on phi, replace that by a continuous coordinate x. So at each position in space, you'd now have a different species of matrix, if you like. So D would now definitely be infinite. So I don't know. So we made so much use of what mathematicians know about these rings. I absolutely am certain that no mathematician has studied the case that will be relevant for 1 + 1 dimensions.
Also, Robert,
Yeah.
I've heard about these matrix models being, I don't know if this is correct, I just want to check. They are sometimes found via dimensional reduction of n = 4 to be animals, right? Or is
That's
that
right.
okay?
No,
Okay.
that's absolutely correct. So if you take n = 4 and you reduce it down to just time, that matrix model is called the BFSS matrix model, and it's secretly meant to be a non-perturbative description of 11-dimensional supergravity.
Okay. Okay. Thank you.
Sure. Actually, sorry, not supergravity. It's meant to be a description of the full M theory, so even more dramatic.
I wonder
Very
if,
interesting.
yeah, I like this. You know, it's canonical quantization. So in principle, honor students taking quantum mechanics could work with this.
Absolutely.
maybe a nice exam problem to cook up. Okay.
Well, if you are going to do that, so the one question I would like to know, just tell them to count how many secondary invariants at n is 8. That would be nice to do.
On a piece of paper, right?
Yeah. Yeah. 10 honor students, 3 hours. That's about, you know, Mathematica for 4 weeks, right? Amazing. I think that's everything, and we really appreciate you taking the time. I think this was incredibly interesting and got a lot of discussion, and really appreciate it. Thank you so much.
Thanks a lot, guys. Enjoy your weekend.
Okay.